Alright, so today we're going to be talking about something called Taylor's theorem. And last time when we were discussing the Taylor series, we saw that we could represent functions as an infinite sum of polynomial terms. So for example, we saw how we could represent e to the power of x as the sum of x to the power of k divided by k factorial. And to see how we arrived at that, I made a video on the Taylor series, so if this doesn't seem familiar, please reference that. But we saw how we can take functions that are not necessary, or like any arbitrary function, and we can convert it into an infinite sum of polynomials. And this equality holds for any x where this convergence holds. And we also kind of discussed that if we were to truncate this infinite sum, where, for example, if I were just to take the sum of the polynomials from k equals 0 to 3 of x to the power of k divided by k factorial, this would be an estimate of e to the power of x, and this estimate would be um, much stronger, or like, well, it would be a better estimate around x equals 0 because that is our center in this case. And as we move away from x equals 0, our error between the actual value, so the actual value of e to the x, and or I can call this like x sub I, where we're plugging in like a random number x sub I, and the sum of the value that you get when you evaluate this summation of x sub I to the power of k divided by k factorial, that error increases. And to kind of see that, I would advise you guys to graph e to the power of x, and then graph these Taylor polynomials that are not the infinite sum. So this is when we kind of limit our upper bound to some finite constant. This is known as the truncated Taylor polynomial. And essentially, as we increase the upper limit that we truncate to, the truncation error decreases. We kind of saw that empirically, and like vice versa, as this value gets lower and lower, our truncation error increases for whatever other constant that we're looking at in this interval. And so far we kind of only looked at that empirically through graphing these these truncated Taylor polynomials that are supposed to estimate the original function. And again, if you want to see like a very concrete example, I'd advise you guys to look at the other video or graph out both e to the x and various truncated Taylor polynomials of e to the x on like Desmos or something, and then you can see how the error kind of increases and decreases corresponding to where we truncate. But back to a point, we kind of saw all of this empirically, where we saw how the errors increased as you moved away from the center, and the errors also decreased as you increased this truncation limit. But how do we formalize all of this and all of that? And what I mean is, the main question is, how do we know how large our estimation error is? Because at the end of the day, only this infinite series perfectly represents the original function. Anytime you truncate, it's not going to perfectly represent the original function. It will be an estimate of it. And rarely are we going to deal with the infinite series because, representing anything infinitely is not ideal, or it's like not feasible. So we'll deal with truncated versions of the Taylor polynomial because polynomials are usually easier to deal with than other functions. And so we deal with the truncated version, and when we're dealing with that, we are inherently estimating. And so when we estimate, one of the biggest things that we want to know is how bad our estimation error is. So how do we know how large our estimation error is? And so that's the main question that is answered by our Taylor's theorem. So answered by Taylor's theorem. So essentially, Taylor's theorem gives us a bound on how bad our estimation error will be on a certain interval. So before I get into introducing Taylor's theorem, let's kind of understand this whole idea of estimating our truncation error through the geometric series, because that's more familiar and I think it'll give good intuition. So assume we use the polynomial 1 plus x squared plus x to the power of 4 plus x to the 6 to approximate 1 divided by 1 minus x squared. And I kind of already mentioned it, but this is basically a representation of, or 1 over 1 minus x squared is just equal to the infinite series of x is equal to 0 to infinity of x to the power of 2, or this should be I, sorry. So I is equal to 0 to infinity of x to the power of 2i, right? And this just comes from the fact that this summation on the right represents a geometric series, and the geometric series converges to this value when the absolute value of x is less than 1. So this equality holds on this domain, and we're assuming, well, okay, so I should have specified this, but we're assuming on the interval of -1 to 1. And so given these facts over here, that we're using this truncated polynomial to approximate 1 over 1 minus x squared on this interval, and given the fact that we know that 1 over 1 minus x squared on the interval between -1 and 1 is simply this infinite series, we know that this polynomial that we're using to estimate 1 over 1 minus x squared is the truncated polynomial of or it's a truncated version of the polynomial. So we're again estimating the truncated error, right? And so if you kind of think about what this series represents, we know that the actual value of 1 minus 1 divided by 1 over 1 divided by 1 minus x squared is equal to 1 plus x squared plus x to the power of 4 plus x to the power of 6 plus x to the power of 8, 10, 12, and then plus x to the power of 2n, and then so on to infinity, right? And what we're using is our estimate, so I'll call this e of x, where e is like the estimating function, is 1 plus x squared plus x to the power of 4 plus x to the power of 6. And we can kind of see this now, that if we were to use the estimating function to kind of estimate the value of this original function over here, what our estimate would be missing would be the rest of these terms, right? So if I were to subtract, so the error between the original minus the estimate, so if I call this function f of x, so f of x minus e of x, this is our error. That is simply the difference in these two summations, right? And so the error would just simply be x to the power of 8 plus x to the power of 10, and then so on to infinity. And the good part about this is we can represent this summation as another geometric series with just the starting term being x to the power of 8. And because of that, we know that since this is just another geometric series with just a different starting term, this converges to the value of x to the power of 8 divided by 1 minus x squared. And hence, that is our error. Another thing to note is that when we're concerned with error, we don't really care about the magnitude of the error. So we don't care about if e of x is greater than f of x or not. We just care about like how big or small the error is. So we write an absolute value. And so when we sort of append these absolute values to all these terms, we get this sort of absolute value function. But in this case, because all our terms are squared terms, this will always be positive. So we can just write it over here. But when I just want you guys to note that whenever we care about error, we just care about the absolute difference, not necessarily the exact difference. So yeah, so our error is x to the power of 8 divided by 1 minus x squared. And this sort of gave us a exact mathematical value of how big our error will be if we sort of try to estimate a value for x using our estimating function, where x is between -1 and 1. And so that's exactly what the Taylor theorem will try to get at. So this in this like the geometric series, the reason I started off with this example is because we can use the tools that we know about geometric series in this case to find out an exact formula for the amount of error we get at a particular point x. But how do we handle? So this was a geometric series, but the question is, how do we find truncation error for non-geometric series? So hopefully, like this motivating example kind of showed us like what I mean by finding truncation error. It's trying to find out the amount of error when we use the estimating function or like the truncated polynomial, also known as the estimating function, to estimate a certain value of the actual function. And in this case, this will be our error. But how do we do this for a non-geometric series? And that is what the Taylor's theorem answers. And so with that, I think we're ready to understand the Taylor's theorem. So Taylor's theorem. So before getting into the exact theorem, note that every truncation splits a Taylor series into the Taylor polynomial and the remainder. And we'll call the remainder R n of x, and we'll call the Taylor polynomial P n of x. And so this Taylor polynomial is our approximating function, and the remainder is the rest of the function, or the rest of the terms in the infinite Taylor series that is left over, and that will form our error bounds. And therefore, using these like splits, what is our bound on the error? So that's what Taylor's theorem is going to answer. So Taylor's theorem says that we know that f of x, if it has derivatives on some interval I, so if f has derivatives on interval I containing point A, then for each x, we can write f of x as f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared divided by 2 factorial, and so on. And this comes just from like our Taylor series definition. And let's say I'm using up to these n plus 1 terms, or in other words, I'm using the nth order Taylor polynomial to approximate our function. Then the rest of the terms can just be summarized as r of n plus x. And what the Taylor's theorem tells us is that r of n of x is equal to f of, or the f of the n plus 1 derivative of f at evaluated at point C divided by n plus 1 factorial times x minus a to the power of n plus 1 for some C between x and a. So what this is saying is that, let's say we have used a truncated, so whenever we use an approximating Taylor function, we're truncating at some term. So that term, the terms that form the Taylor polynomial is going to be known as p of x or pn of x, and this part corresponds to pn of x, and then the rest of the terms in that infinite series form the remainder. And in this case, what we're doing is we're centering our Taylor polynomial at point A, and we're estimating for some value of x. And now what Taylor's theorem tells us is that our remainder, and in this case the remainder and the error is, well, the error is going to be the absolute value of the remainder, but like you can, for all intents and purposes, you can kind of think about the remainder as the degree to which we misrepresent what the actual value of the f of x function is through our truncated polynomial. That value is simply, basically this would be the next polynomial term in the Taylor series, but it's evaluated at some point C, and C is just between the centered point and whatever x value you're choosing. So if x is to the right of C or x is to the left of C, it's in C is chosen in that interval between A and wherever the x is. And that formulates the error term, basically, for a Taylor polynomial. And the reason why it's a random term C between x and a is because we want to get the largest bound on the error. And the largest bound on the error could be anywhere between x and a when we're trying to estimate using our truncated polynomial. And therefore we have C instead of using the value simply at x. And just in terms of notation, this first part, so P, the part that gives us Pn of x, so this part which I underlined earlier, is called Taylor's formula. Then this is the nth order remainder. Slash error term, and sometimes it's also called the Lagrange form, or the Lagrange error bounds. So knowing all of this, we can finally kind of give a mathematically precise way of saying what it means for a Taylor series to converge to a function on an interval. In other words, if the nth order remainder converges to 0 or tends towards 0 as n tends towards infinity for all x in the interval I, then we say the Taylor series generated by f at x equals a converges to f on I. And we can write f of x is equal to the sum of k equals 0 to infinity f to the kth derivative of a divided by k factorial times x minus a. Okay, and so this final part is just for like mathematical preciseness. What I'm saying is that if the remainder tends towards 0 as I'm taking higher and higher nth order remainders, it means that whatever our estimating Taylor polynomial is, it actually converges to the true value of f of x in that interval. And therefore, if you were to find the formula for the remainder, which we get through this, and we see that it's not converging towards 0 as we increase n, then our Taylor's polynomial does not converge for that specific x value. So knowing all this information, let's do some problems, because I can kind of understand that this was very, very abstract. So the first question is, prove that the series of k is equal to 0 to infinity of -1 to the k x to the power of 2k plus 1 divided by 2k plus 1 factorial converges for sine x for all real x. So we know that this for like this series over here represents the Taylor series for sine x. Just recall that from the previous video. And now we want to prove that for all x values, this convergence holds. So sine x is equal to, we want to prove the equality between sine x and the infinite polynomial. So we need to consider what happens as r of n of x as n tends to infinity to actually prove convergence. And so by the Taylor theorem that we saw earlier, Rn of x is simply equal to f of n plus 1 at some point c divided by n plus 1 factorial times x to the power of n plus 1. And so we want to calculate the limit as n tends to infinity of that function. Now, the one good part about the fact that this is a sinusoidal function is that we know that this derivative will always be either like sine x, cosine x, or like the negative of that, right? And so we can bound this value between 1 and -1. And when we can do that is because we can do that, we can get the fact that the limit as n tends to infinity of the absolute value of that term is simply between the absolute value of like, right? So that will just be 1. And then x to the power of n plus 1 divided by n plus 1 factorial. And then I can just treat this as 1 as the maximizing value. And so this I can just remove and act as a coefficient. And now I just have to compare how x to the power of n plus 1 grows compared to n plus 1 factorial. And so the top function is a power function, where the bottom function is a factorial function. And the factorial function grows much faster as n tends towards infinity than the power function. So our limit tends towards 0. And because of the fact that our limit tends towards 0, we can state that this series does converge to sine x, because our remainder tends towards sine x. So what we did over here in this case was that we upper bounded what the value of this nth derivative will take, and that really allowed us to finally give a convergence value. And that practice brings about another theorem, and that theorem is called the Remainder Estimation Theorem. And what the remainder estimation theorem basically states is that if there are positive constants m and r such that the absolute value of the nth derivative at some value t is, or for all values t, are always less than or equal to m times r to the n plus 1 for all t between a and x. so a is your center and then x is like the value you're trying to estimate, then this equality holds true. And so this just formalizes what we did before, where we're just substituting in the value of an upper bound for this derivative instead of dealing with the derivative itself, because that helps us come up with convergence proofs, or helps us prove that the limit converges to 0 or not converge to 0. So this is just what we did in the last problem, but restated in a more formal way, so hopefully it's not too confusing. And let's kind of use that fact to prove, now let's prove that e to the x is equal to this this Taylor series for all x. Now, basically, the idea is we have to sort of form a bound on the remainder, right? So we know that simply r of n of x is equal to, or the absolute value, which is the bound of the error, is simply the absolute value of the n plus 1 derivative t times x minus a, where in this case a is just 0. So x to the power of n plus 1 divided by n factorial. And we know that this function, because we're dealing with e to the x, is always going to be e to the x. And the largest value, e to the x, takes on an interval between a and x, is simply e to the x, right? Because e to the x is an increasing function, and if we have the center at a and x is some value greater than a, or yeah, a, then that's the largest value that e to the x takes on. So we can write this simply as e to the x times x to the n plus 1 divided by n factorial. We already know that, or this should have been n plus 1 factorial actually. And we already know that from before that the factorial function grows faster than the power function, but the factorial function also grows faster than the exponential function. Because if you kind of think about this, okay, this is not even a growth as a, this is just gonna be some constant, right? So you can just treat this as a constant that's just dependent on x and not dependent on n, and we know clearly that the limit as n tends to infinity from the argument before of x to the power of n plus 1 divided by n plus 1 factorial times e to the x will simply be 0, because this is a constant and then this power function grows slower than our factorial function. Alright, so we did that proof. Let's do one final problem. We use the approximation of ln1 plus x for x minus x squared divided by 2. Let me just say, find the maximum error where the absolute value of x is less than or equal to 0.1. So we're using this approximation on this interval, and we want to find the biggest error we get between using this approximation and the actual value of the natural log of 1 plus x. And so let's use the remainder theorem. Since this is up to a second order, the remainder theorem tells us that R2 of x is simply equal to f of 3 at some point c times x, and the center is 0, so x to the power of 3 divided by 3 factorial, and therefore we just need to find the third derivative. Third derivative is f prime of x is 1 over 1 plus x. F double prime of x is equal to negative 1 over 1 plus x squared, and then f triple prime of x is equal to 2 divided by 1 plus x cubed. Knowing that, we can plug in what we know. So we get 2 divided by 1 plus x cubed times 3 factorial, which is a 6, times x cubed. And this should be 1 plus c cubed because this is at some point c, and we want to kind of find the maximizing value for 2 divided by 1 plus c cubed. And we know that on the interval between x being since we know the interval is x being greater than or equal to -1 and 0.1, and judging by this function, as x increases, this denominator increases, and therefore the value decreases. So the maximizing value is at x is equal to negative 0.1, and so that is our c value. So therefore we get that the highest error bound is simply at 2 divided by 3 factorial times 0.9 cubed, because 1 plus negative 0.1, and we now have to multiply by x minus a to the n plus 1, and its largest, well, the largest, like the way that we maximize x minus a is if x is a large value, and that's simply at the largest value that x can take on away from the center is just at 0.1, so we have 0.1 cubed. And then we divide that by, or we already have that divided by 3 factorial. And so essentially what we end up with is this is equal to 2,000 divided by 729, because this evaluates to 0.729, times 1 divided by 1,000 times 6, because of the 3 factorial. And if you were to evaluate this out, this is less than 4.6 times 10 to the negative 4. And so this was an example of us finding an actual numerical bound on the maximum possible error in that interval. So that was the use of the remainder theorem.